Okay. So we're heading into the world of continuous random variables. Now, what's the difference between a continuous random variable and a discrete random variable? Well, the reason why a discrete random variable, not continuous, but discrete, the reason why a random variable was called discrete was because the values of that random variable, like many times our values were like 0, 1, 2, 3. So this set contains a discrete number of numbers. They're countable because I can count them. They're not infinite, they're finite, but they're discrete because I can count them. And then we've also had other scenarios where, for example, the geometric random variable, right? That one was 0. No, that one doesn't start from 0. It starts from 1, 2, 3, dot, 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 and goes on forever. This is also considered discrete because each of these values obviously can be counted using the counting numbers. Now, the issue arises when the value, for example, of x is contained in an interval from like 0 to 1, for example, which could happen. What if the values of my function x are anything between 0 and 1, as an example? Now that becomes continuous because the numbers between 0 and 1 in the interval, right, from 0 to 1, all of these numbers here are in a continuous medium. You can think of a continuum. You can't count all these numbers either. There's uncountably infinite numbers. So that's when we head into the world of continuous random variables. So in this new phase of random variables, a bit of calculus will be introduced and revisited. So we're gonna use a lot of integration from this point on. Okay, and so the first thing is a little bit of notation here. In discrete, in the recall, let's just recall a little bit. In the discrete, let's put recall. Recall that in discrete world, right? What do we have? With discrete random variables, we have a PMF, right? And that PMF was defined as what is it? It's the event that x equals, for example, I for some value I, right? And we denote it as P of I. So this was the PMF, correct? The probability mass function. In discrete world, we don't have a PMF. We have what's called a PDF. We have a PDF, and this stands for the probability density function. So that the M originally for discrete is now a D. So this is probability of density function. And we just give it f of x. That's what it's equal to. F of x will be particularly used for denoting a probability density function. And the way we evaluate probability with continuous random variables is through integration. So for example, so they give you kind of notation like this. So the PDF, right? The PDF is if the probability of the random variable being contained in a set. So B is a set. B here is like an interval or a set, right? But that's continuous. Again, this is continuous. So this equals the the integral of the set B, whatever that is, defined on B of f of x dx. Okay. And of course, we have that if we add up all the probabilities along the interval from negative infinity to infinity, so if we evaluate the integral from negative infinity to infinity of our probability mass function, guess what this all has to add up to? One. Right? This has to add up to one. All the probabilities from the density function, when you add them up from negative infinity to infinity, the idea of continuous random variables is when you add them all up, it always gives you one. The same way as if you're in a discrete case where you have a discrete number of values, and for the probabilities for each of those values of the random variable, when you add them all up, they equal one. Now, the only difference is instead of dealing with discrete, we're dealing with a continuous set of numbers or set of values. That's the difference between continuous and random variables. So that's the first thing. Okay, so as an example, suppose x is a random variable, is a continuous random variable. And I want to find a probability that my random variable is between an interval such as a to b. So again, from now on, continuous random variables, we're going to be dealing with a range of values for x, which is much different than what we experience in discrete random variable world. Is that capital X? Yes. Yes. So x is the random variable, and I want to find the probability that the random variable x is the values of x is between a and b. Okay. So how do we calculate this? We would take the integral from a to b of our probability density function f of x. So again, this is just an example of what would happen if our random variable, if I want to calculate the probability of our random variable between two values, a and b. Okay. So because of this, as a result, you guys think the probability that x equals a particular value k, for example? Does anybody see what can happen here? That's right. Very good. You can think of this. You can think of this as saying x is between k and k, right? Like, even though we don't do this, we can write it this way, which would indicate that this would be the integral from k to k of a function. And again, this idea of continuous random variable, right? We're dealing with a continuous function. The probability density function is normally continuous. It's a continuous function in itself. So we're taking the integral from k to k of a function. What do we know in Calc 2 that if we take the integral between between the integration bounds being the same thing, what's the result of that? What's the result? Zero, of course. Of course it's zero. Of course it's zero. You can think about it as the area underneath a function, right? Good. I'm glad your brain worked, Alexandra. Think about the area underneath the function f of x, but the x interval is a single point. It's like a dimensionless area, which is zero. So like if you consider the function, for example, like just a random function here, let me just write this as y equals f of x. And I want to calculate the area from k to k, but it's just a straight line. It's just a straight line. The area of a straight line is zero. No matter how long this line is, you can't calculate the area of something that's dimensionless. There's no two-dimensional. It's just one-dimensional. So the area in this case is considered to be zero, right? And then if we have something between a and b, what are we actually doing? We're calculating the function here. So this would be the probability that my random variable is from a to b. So now we're kind of extending this idea of area, right? Normally in Calc 2, you just talk about calculating the area, using integration, calculating the area. But now this calculation of the area is really calculating probability. So sometimes you can make that connection now that calculating probability is, or calculating the area is calculating probability. Calculating probability is calculating area, which is pretty cool when you make that connection. It goes beyond just a numerical computation. It's now geometric as well. Okay. Good. So associated with the probability density function, so always try from now on, try to relate what we learned in continuous random variables with discrete and see the difference. So we've spoken in discrete random variables regarding probability mass functions, and now we have probability density functions. What's the difference? Well, one of them has discrete values for which the values are attained, right? 0, 1, 2, 3, for example. But in continuous, with the probability density function, my function now produces numbers that are in an interval. And this is an uncountably infinite set of values. When we calculate the probability using the probability mass function of discrete random variables, we're just calculating the probability of a single value and knowing what that probability is. And in continuous random variable world, we're calculating an infinite number of probabilities. And in order to do that, we're utilizing the integral operator that we use in calculus. Because if you remember, the integration symbol actually, I don't know if you guys were shown this, but the integration symbol in itself is a elongated S. It's a sum. It's an infinite sum. When you guys remember the Riemann sum, right? When you talked about the Riemann sum, this is when you take the limit as n goes to infinity and you're taking an infinite sum of smaller and smaller rectangles of area. So that's what we're doing with continuous random variables. So there's a PDF continuous world, there's a PMF in discrete world, there's a CDF, right? A cumulative distribution function in discrete random variable world, and there's also a continuous a cumulative distribution function in continuous random variable world. So we do have what's called a CDF, which is a cumulative distribution function. And it's defined the same way. It's the probability that your x value is less than or equal to some kind of value a, right? And we call this f of a. And this equals the integral from negative infinity to a of my random variable f of x dx. Or pardon me, my probability density function f of x. So we're accumulating all the probabilities from the values being negative infinity all the way up until what a is. Okay, and let me just make a note that the PDF f of x is a real valued function defined on negative infinity to infinity. So that's pretty important. The function, the probability density function, is defined on the interval negative infinity to infinity. That's why we always deal with negative infinities or infinities when we talk about the all of the values of what f of x can be. And theoretically, it could be the x values that we plug into our probability density function, and theoretically it could be anything between negative infinity to infinity. Okay. So what? So sometimes, for example, you'll be given a probability density function. So given the PDF of x, so the PDF, for example, I can call it f of x. This equals some piecewise function. And this is c of, let's see, 5x minus 3x squared. And this is when x is between 0 and 3. And it's 0 otherwise. So I'm being given a probability density function of some continuous random variable. This is what it is. So when my x values are between 0 and 3, I have this value for the probability density function. And when my x values are not in this interval, then it's just 0. And then the question is, what value of c, what value should c equal? Should c be? So this is a typical question about continuous random variables. And so given what we know about continuous random variables, what fact can we apply to this scenario in order to figure out what c would be? What do we know about continuous random variables and their probability density function? What do we know? Whenever you don't know something, you always try to figure out based upon what you do know. We know that if we take the integral from negative infinity to infinity of any, doesn't matter, of any probability density function from negative infinity to infinity, it must equal 1. That must be the case, and it always will be the case. So that's good, because I do know the value of my function. So I do know what it looks like. It looks like negative infinity to infinity. And if you really want to break this down correctly, you can break this down like this: negative infinity to 0. But what's from negative infinity to 0? What is f of x when my values of x are between negative infinity to 0? Well, according to the way this is defined, it would be 0, right? My function is 0. And then I'm adding from 0 to 3. the function c 5x minus 3x squared dx plus from 3 to infinity 0 dx. Does everybody follow that? I just broke down, I split up this integral from negative infinity to infinity into 3 intervals. But as you can tell, when I speak about the otherwise condition, meaning that I'm either bigger than 3 or when I'm less than 0, my probability density function is 0. It's still defined. My function is still defined on the values bigger than 3 and the values less than 0. It's still defined, but it's defined at being 0. So it's like it's like a constant function 0, and the area underneath the constant value is 0 for an infinite interval will also be 0. So actually we don't need that part anymore. We only need that the integral from 0 to 3 of c 5x minus 3x squared dx, this equals 1. So that's all that really matters. And then as we move along, we can factor out the c. This becomes 0 to 3, 5x minus 3x squared. And from here, we have a standard well, it's a definite integral. So we can apply the anti-differentiation techniques here. This becomes 5x squared over 2 minus 3x squared over 3, 3. So this just becomes x cubed, defined at 0 and 3. And this entire thing is being multiplied by c, which equals 1, right? And so we plug in the numbers. 5 times 3 squared over 2 minus 3 cubed. And then when you plug in 0, it doesn't really matter because it becomes 0. So we don't have to worry about that. And this becomes 5 times 9 over 2 minus 27. And then this becomes 45 over 2 minus 27. And if you multiply this by 2, you get 45 minus 54 over 2. That equals c, equals 1. So c is equal to, I should say c times negative 9 over 2 equals 1. So c is equal to negative 2/9. So we found what the value of that constant c should be to produce a legitimate probability density function, which is dependent upon the fact that the integral, the improper integral from negative infinity to infinity of f of x always has to add up to 1, always and forever. Okay, so then finally we have what? Finally, we have that our probability density function is equal to negative 2/9. What was it? It was 5x minus 3x squared when x is between 3 and 0, and this is 0 otherwise. Okay. Okay, does that make sense, guys? Any questions thus far about probability density functions? Yes, yes, yes. Okay, great. So let's move on to the next thing. So let's talk about particular examples. So these are like examples of discrete, continuous, pardon me, not discrete. Continuous random variables. So we'll start with the most basic one that exists. So remember in discrete random variable world, the first one we spoke of it being a particular type. So yeah, let me instead of example, let me write types. So the Bernoulli random variable was the first discrete random variable that we discussed, and it was whether you had a success or a failure in a particular trial. And when you have a success, we said that the value of the random variable was equal to 1, and when you had a failure, the random variable was equal to 0. And based upon each of those values, they had a particular probability, and that probability was called p, and that p value was between 0 and 1, and so the probability for the failure would be 1 minus p. So that was a very simple discrete random variable. Now we're going to deal with the simple case of the continuous random variable, which is reminiscent of the Bernoulli, and it's called the uniform random variable. And this uniform random variable is usually defined upon a interval a to b. So it's defined on a to b. So what are we speaking of? We're speaking about a interval from a to b on the number line. So consider the number line. We have an interval from a to b. And so we want to figure out what's the probability that my random variable x is on this interval a to b. So what does that mean? So what is the probability of this random variable from a to b? So I would have to calculate the integral from a to b of f of x dx, right? So before we deal with the general case, let's look at the more specific case. So more specifically, we say that a random variable x is uniformly distributed over the interval 0 to 1 if the PDF of x is, so we do f of x, it's almost another piecewise function again. Very simple though. It's 1 if my x values are between 0 and 1. And it's 0 otherwise. Now, just to make sure that this makes sense, right? This is okay because just you can check yourself. If I take the integral from negative infinity to infinity of this function f of x, I should get what? I should get 1. So what am I actually computing? What am I actually dealing with? So what is this function? Can I graph the PDF? So now we can graph PDFs as if there were regular functions that we normally would graph in other more basic math courses, right? foundational math courses. So from 0 to 1, what does that look like? Looks like having a constant function from 0 to 1. This is 0, this is 1, this is 1, and we have something like this. This is my PDF. My PDF is literally a straight line from 0 to 1. That's all it is. And this area here is 1. And what I'm saying is that for every value of x between 0 and 1, the probability is 1. It's a little strange to think of it this way, right? From the discrete world that we're currently in and now into the continuous world. But for every value here, for every single value from 0 to 1, the probability mass function, the probability density function is defined to be this way. It's equal to 1. And this is consistent with saying that the infinite sum, right, of these values, when you add them up, they give me, they're equal to 1. Okay? So this is the simplest of the simplest kind of random variable, and we call this a uniform random variable. And this word here, uniformly distributed, becomes very commonly used when they define distributions of probabilities using these kind of terminology, uniformly. So when you see the word uniformly, you have to think about the PDF being in this fashion. So when this is the case, what happens when I say that the random variable is uniformly distributed on AB? So now we say that x is a random variable uniformly distributed on AB. Now some other, you know what, let's make this a specific one. On, let's say it's 1 to 3. Then the PDF would be what? Then the PDF would be what? What would be the PDF? Well, the x values are between 0 and 1 and 3. So this would have to be 0 otherwise. But we don't know necessarily at this moment, unless somebody does know, what would be the probability? What would be the function defined from 1 to 3? It would equal 1. So if you say this is the case, if this equals 1, right? If this equals 1, then when I graph this function, right? Remember, we can graph these functions because they're continuous. They're continuous functions. So we're graphing this from 1 to 3. And according to you, Fang, you're saying this is from 0 to 1, right? But if we calculate the negative infinity to infinity integral from f of x, what would we get from 1 to 3 if this is 1 dx? What would be the integral here? Wouldn't it be 2? Isn't the integral from 1, like, isn't the integral of the constant, that of function 1 from interval 1 to 3, isn't this a rectangle whose dimensions are 1 by 2? And isn't this area wouldn't this area be 2? But isn't this not a good probability density function because it's not supposed to equal 2? It's supposed to equal 1 at most. So we have to change this. This can't be 1. What is it? Well, let's say we don't know what it is. It does have to be a constant though. Yeah, so Alexandra, you're starting to understand this, right? So this is, let me call this constant C. We can actually figure out what it should be. What should it be? I'm gonna call this C. Well, I know that if I take the integral of negative infinity to infinity of my probability density function, this should give me 1. And I know that this function is only defined between 1 to 3 of a constant value, which I don't know. And this has to equal 1. But what do I know? I know that this will equal what? 2C, which equals 1, because C is a constant, and so it's just 1. So it's 2C. And then C has to equal a half. So actually, C is 1/2. So for every value that's defined here, my probability density function jumps to a half. Does everybody see that? So now that I defined a legitimate probability density function, now it's clearly defined. Look what I do is the following. I can say, what's the probability that, okay, let me say this. What's the probability that x equals 2? Can anybody tell me what's the probability that my random variable x is equal to 2? This should be quick because this is a continuous random variable. No, so Mir, it's not that it's 1/2. The probability density function is 1/2 when x equals 2. But what's the probability that my random variable equals 2 is not 1/2, but it's the integral from 2 to 2 of my function being 1/2 dx. But this always has to be 0 because I'm defining the variable, the integration between a single point, which that area would be a width of 0. So the area would be 0. So whenever you're dealing with a continuous random variable and you're finding the probability of a continuous random variable equaling a single point, the way we're defining this now, we should know that the probability of a random variable equaling a single point is 0. But when I make this a range of values, a continuous range of values, for example, if I make this instead, that what if my x values between 1 and 2, what would this be instead? The probability that my random variable is somewhere between 1 and 2, somewhere. So then I would have to use the probability density function from 1 to 2 of 1/2 dx. What is this going to be? Do you guys see that? So when you evaluate this, what does this become? 1/2, right? So the probability that my random variable attains the values from 0 to 2 is a half, which would be the same thing as looking at this graph here and finding the area of this very simple rectangle whose dimension is 1/2. You guys see that? So now we're going to be heading into a kind of world of random variables where the area is very important. Oh, so P, yes, that's something I think I should have mentioned earlier. So note that the probability of the x value being less than or equal to 2, less or greater than or equal to 1 is the same as the probability that x is less than 2 and less than 1. It's because of the fact that at 2 and at 1, at a particular value, the integral is 0 at a width of, so this less than or equal to symbol or less than symbol is not really that, it's not much of a difference when we calculate the integral of it. It's not a difference at all. It's a dimensionless difference. If I include one or if I don't include one, I'm just getting rid of an area that's zero. That's what I mean. So it doesn't make much of a difference in this world. In the world of it's like, yeah, it's like saying I'm gonna include this line or I don't include this line. The area still stays the same. It's still the same. In the world of discrete random variables, this matters a lot. In the world of continuous random variables, it doesn't matter so much. Okay, that's a great point. So then what would be the probability of what we originally started with, of a random variable being uniformly distributed on the interval 0 from A to B? So now a random variable uniformly distributed on some random on some interval A to B has a PDF of what? So my PDF is some function that is 0 on any value outside of the interval A to B. And if my values of X is between A and B, what would it be? What would it be, guys? Let's say we don't know. What do we know? We know that it equals some constant, right? That's the way the probability density function of a uniform random variable would be. And so that's right, Fang, that's right. So what we do is we take the integral from -infinity to infinity of f of x dx. We know that this equals 1. We know. Then from here, we say that the integral from a to b is some value x c times dx, which equals 1. Then we know that this is equal to what? This is equal to c multiplied by the constant function 1 from a to b. But this is just equal to the area of a rectangle where one dimension is 1 and the other dimension is b minus a, and the area of that is b minus a, which would entail that the constant we're speaking of will be 1 over the length of the interval, b minus a. And so then when we calculate, or when we graph, I should say, the probability density function, it would be an interval from a to b, and the value of my f of x is 1 over b minus a. It's just a constant function from a to b. And so then my probability mass function will be 1 over b minus a whenever my values of x are between a and b, and it would have to be 0 otherwise. And so this would be the probability density function of any uniform random variable defined upon the interval a to b. Make sense? Okay, so then based upon this, what would be the cumulative distribution function? How would you define that? So what would be the cumulative distribution function? So let me call this f of x. So so this is for a CDF for x uniformly distributed on A to B. So if you remember, the cumulative distribution function is just an accumulation of all the probabilities, right? So we're defining f of x again. Remember f of x? F of x is defined as the probability that my x value is less than or equal to some value x, which is the same thing as saying from negative infinity to x of f of x dx. That's what the cumulative distribution function equals. Okay, and so then this has to be it's also going to be represented as a piecewise function, but we have to be a little bit more considerate of what x will be, what x can be. X can be various values, an infinite number of values. X can be anything from negative infinity to infinity. But there's only 3 different scenarios, right? The same way that we created these 3 different integrals up here somewhere, right? So x can be, we can represent x as 3 different things. X could be something less than a. So what if x is less than a? What is the function? What is my probability density function if x is not in this interval and x is less than a? My probability density function is 0. But the probability, if my x value is less than 0, I mean, if my x value is less than a, my function, we're finding the area of a constant function being 0. So the integral of a constant function 0 on any interval will always be 0. So that will be my first function here, 0, right? Now, what if I'm gonna do a simple one. What if x is bigger than b? What if x is bigger than b? So what if I have a function, a value, some of a x value being bigger than b for some value of x, right? Some value bigger than b. Then I'm gonna do the integral of this x. So again, x is bigger than b. What does that mean? That means I take the integral from what? From negative infinity to x of f of x dx. But what is this? I know this already. I know the probability f of x is 1 over b over a, 1 over b minus a. But my x value in this case, my x value, it goes beyond the b value. But this is 0 beyond b. This is 0 less than a. But all of this, I know the area already for this. The area would have to be what? The area is 1. This will be 1. Not 0, guys. It's 1. I don't know if you're responding to the same thing. The cumulative distribution function when x is bigger than b will be 1. Any value above b, any value, no matter where it is, the area underneath the only function that I have here, the area will have to be 1. Again, I'm accumulating I'm accumulating area basically. That's what the cumulative distribution function does. It accumulates area all the way up until a particular point. So if my point is beyond the interval b, my point is beyond b somewhere, right, on this graph, and I'm accumulating all the area up until this point, and all the area here is 0, the area here is 1, and the area here is 0, when I accumulate everything, I get 1 at the end. That's what I'm supposed to get anyways. Yes, Alexandra.
I'm kind of confused by that, just because if you extend the interval along the x-axis, wouldn't the area continuously get smaller if you're looking at the... So I thought the area after b would be 0 because you're not considering the, the area after b. You're just looking at the area between a and b, which is supposed to be 1.
Yeah.
So it's hard for me to understand why the area greater than b, the value greater than b would be 1 forever into the x direction.
Oh, because you're missing the fact that I'm accumulating all the area from negative infinity up until the point x, which is beyond b.
Okay. How is this different than the last example then?
This one here?
Um, I'll figure it out. You can continue, sorry.
Yeah, no. So no, this is good. This is a good question. So I the cumulative distribution function is a function that accumulates area, which is the area underneath the probability density function. So if I'm saying I'm accumulating all the area of my probability density function, my PDF, up until a point where the x value is less than a, right? So we go back to this graph, simple graph that we have. So any value of x, suppose that it's less than a, what would be the accumulation area? Well, all of this is 0, less than a. So that's why when you plug in x for a value less than a, my function is 0, my cumulative distribution function. Now suppose I get an x value that's bigger than the value b, somewhere bigger than b, right? I accumulate all the area from all the way from negative infinity. So our reference point is always negative infinity, will always be negative infinity. And then we're accumulating all the area. Well, all this is 0. And like you said, Alexandra, all of this is 1. You're right. So then when you accumulate everything that's beyond b, any value of x beyond b, the accumulated area will always be 1. Yeah, it will always be 1. So that's that's what's expected. What's expected is anything below a, because all the area is 0, then it will always be 0. And for any value bigger than b, the accumulated value of the accumulated probability density function, the accumulated area will always be 1. The tricky part becomes what happens when my x value is it's exactly in the interval a to b. That's the real issue. So what happens when I have some x value here? Call this here, right? So then what would be the cumulative distribution function defined as here? So how would you find that? And hopefully now you start to see, oh, I can do the integration, right? I can do this whole integration thing, or I can do what? I can find the what? The area of a rectangle whose dimensions are what? What is this dimension here? X minus a. And what's the vertical dimension? 1 over b minus a. So when you multiply these two dimensions, what do you get? You get x minus a all over b minus a. So what's nice about this, at least from the continuous random variable case, is that I know it looks like it's a little complicated with the way we're defining things now that we're dealing with continuous values, but we can sometimes forget about that whole idea of continuous and just think about area. It's a lot easier to consider areas of very straightforward regions than dealing with the context of what do you mean by integral from negative infinity to, like that becomes more theoretically based things, right? Like it's like, why, what does this mean geometrically? What does this even mean? But when we are able to transfer this idea into areas of very simple regions, it becomes a lot simpler to grasp. And then this becomes a lot simpler to get. Again, we can still do this with integration. It's the same idea. But what I'm trying to help you guys is to emphasize the connection now that we have between probability and area. Okay? And so to finish this off, we have to make a little entryway into expectation. So how do you find expectation of continuous random variables? Again, remember what happens in discrete random variable world. So remember discrete. Recall, for discrete, what was the expected value of x? How is that defined? You guys remember? It was defined as the summation of the values of x, right? Multiplied by what? P of x. And of course, there's like some notation here. I goes from, and this can go from to n to infinity, depending upon what kind of random variable you have. Now, segue that, connect that to the continuous. So what do you think continuous random variables would look like? So the expected value of a continuous random variable x instead of summation, we're going to get what? So the summation symbol for discrete is now connected to the integral. And when we calculate the expectation, we're dealing with all the different values of x, right? And again, this is the discrete. That's why we have an n. Sometimes we have a finite number of values for x, or sometimes we have an infinite number of values of x, but it's still discrete. So we're dealing with all the values of x for the discrete case. An integral is an infatuate summation, or did you mean an infinite?
I meant to say infinite.
Okay,
Yes.
that's what I thought.
Like
Yeah.
the discrete is a summation, and then the continuous is also an infinite summation under the integral.
Yes. So you're asking why is it different? What do you mean?
Like how are they different? Is it just the notation and the computation? We're taking the integral
It's
instead of
different.
this.
It's different because here you're adding like you're adding one thing plus another thing plus another thing. With the summation, you're like your accumulation. It's how do you say it's different. Like here you could be adding things like 1 plus like 0.5 plus 1/3. You can be adding this, but here you're adding an area. Here you're adding like points, like points, and like you're adding a discrete number of things. Here you're not. You're adding on aggregate, a holistic thing. I don't like. It's kind of hard to explain that. It's sometimes hard to explain continuity compared to discrete, right? Because it seems like, wait, aren't we saying the same thing? We actually aren't, but inherently we are, because we're talking about sum, right? Here we're talking about a sum of discrete things. Henceforth, we use summation symbol because it's discrete. You can't add discretely things that are continuous. You can't do that because then it's inherently different. It's a different nature of things. Well, something is discrete, we can pinpoint, say, okay, this is one thing, this is another thing, this is another thing. Let's add them together. That's summation symbol. Here, we're taking, if you consider the integral and the definition of the integral using the Riemann sum, you're taking a limit as n goes to infinity of a discrete sum. That's why it's so magical. This limit, this little thing here is magical because it creates something new. It goes from the discrete world into continuous world, and which is hard to determine and understand what that is because we don't live, we don't know necessarily how to deal with continuous things all the time. We're dealing with discrete things. We can talk about, oh, this is one book, this is one room, this is like two computers. Like we can talk about discrete things very naturally. When we talk about continuous things such as time, temperature, like these continuous quantities, it's a bit more involved. But anyways, the integral would be what? From negative infinity to infinity of x multiplied by f of x dx. Do you see the similarity? Summation symbol, integral symbol. All the x values that we're dealing with, all the values of x that can be attained, right? There's a discrete number here. The number of that x values can be attained here is infinite, uncountably infinite, no longer discrete. P of x is the probability mass function for my x random variable attaining the value x. And this is my probability density function for every value of x. So you see how they look very much the same. This is the discrete world. This is continuous world. Okay. So then can we apply this to find the expected value of a random variable? So what is the expected value of a random variable x normally distributed on A to B? So I want to find the expected value of my random variables. So again, we're going to be dealing with random variables. We're going to be finding out the PMF for discrete and the PDF for continuous. For every one of those random variables that we speak of, there's a particular way to find the expected value. So we should know the expected value of every kind of random variable and also the variance of every type of random variable. So using the definition of expected value for continuous random variables, we can find the expected value for any uniformly distributed random variable or any uniform random variable on AB. How do we do that? Well, we apply the formula, the definition for expected value, which would be what? Negative infinity to infinity of x times f of x dx. That's what it is. But on a, recall, we just talked about this, recall that f of x is equal to what? 1 over b minus a when x is between a and b and 0 otherwise. So I don't really care about the x values beyond b nor less than a because I get a constant function 0. So this integral becomes what? It becomes the integral from what? A to b of x times 1 over b minus a dx. Right? And now finally you see this is going back to Calc 2 now. Calc 2 integration, it's going to come back again and again. So 1 over b minus a can be factored out, can be taken out of the integral, and I'm left with a to b of x dx. But that's just finding the antiderivative of x, which is x squared. X squared is between what? B and a. Evaluated at b and a, 1 over b minus a. So this equals what? This equals 1 over b minus a multiplied by b squared minus a squared, which is equal to b squared minus a squared all over b minus a. So then what does this become? B plus a, b minus a over b minus a. So then when you cancel out the b minus a's, what's the expected value? The expected value is going to be b plus a, right? Or a plus b. But we're missing something, aren't we? What are we missing? Does everybody see what's missing? I just noticed that when I was at the end of this. No, nobody notices. The antiderivative of x is not x squared, it's x squared over 2. There's a division of 2 here the whole time. So there's a 1/2. There's a 1/2 being applied here. So a plus b over 2, that should be the expected value. And this should make sense. Why should this make sense? Because remember what expected value can also be interpreted as, and we spoke about this very briefly using the PMF. Was that from A to B, right? We have this constant function. And because this is a very symmetric, this is a very simple region here, it's a rectangle. Remember the expected value was, you can consider it as a point along this, the graph of the PMF that would balance out the probabilities. So think of this as a block instead. Now, remember PMFs were like little graphs, little bar graphs, right? They're like bars. So then think of those bars having weight, and then you stick the expected value as the place where you put the little fulcrum so you can balance out the weights. This is the same idea here, but now think of the weights not being as particular discrete bars, but now it's one single block here. And this block has a weight. Where would you place the fulcrum so as to balance out this weight? You would put it right smack dab in the middle, wouldn't you? So this is exactly where the expected value would be. The expected value is smack dab in the middle. This is going to be A plus B over 2. That's what A plus B over 2 is. It's the average of A and B. So the average of the uniform random variable defined on A to B is A plus B over 2. So this idea of having the center of the mass, center of mass, and that connection with the expected value, it also coincides with viewing that from a continuous random variable standpoint. So you could have also come to this conclusion without having to do all this integration. You could have been like, where would I place, what would be the place that balances out the weights distributed on this region here? It would be smack dab in the middle of the interval. So that's another way. So it just makes sense. Okay. So this is the case for every uniform random variable. The expected value will always be the sum of the endpoints divided by 2, which would just be the midpoint between A and B. Okay. And then last but not least, we'll also talk about the variance. So what would be the variance? So what is the variance? What is the variance of X for a randomly, for a random variable uniformly distributed on A to B? So what is variance again? Remember variance? There was two definitions of it. X is either the expected value of X minus mu, which is the expected value squared, or we can define it as what? The expected value of X squared minus the expected value of X quantity squared. Remember this? Well, the thing is, we already found what this is, didn't we? Like, we already know what this is. This is exactly what was found up here. This is A plus B over 2. So all I have to do now is square that. And now I have to find this. What is the expected value of X squared? Now, how do we do this? It's a little bit easier, I would say, with continuous random variables than discrete random variables to find it. It's easier because it's just an integral problem. It's negative infinity to infinity of what? Of X squared f of X dx. It's no longer, the expected value is not just going to be X, it's the expected values of X squared. So this function here would be, this little thing here, instead of it being X, will be X squared. Now what's f of X? Is 1 over B minus A. from A to B. And so this will be 1 over B minus A of the antiderivative of x squared is x cubed over 3 evaluated from A to B. Right? And this will equal what? 1 over B minus A multiplied by B cubed minus A cubed over 3. But do you guys remember what this factors into? This is a difference of perfect cubes. So this becomes 1 over B minus A multiplied by B minus A multiplied by B squared plus AB plus A squared over 3. The B minus A cancels. And so then my notation here would be B squared plus AB plus A squared all over 3. That's the expected value of x squared. But I want to find the variance. And what's the variance? It's the expected value of x squared minus the expected value of x quantity squared. I know what this is now, b squared plus ab plus a squared over 3 minus the expected value of x. What was found? It was found to be a plus b, a plus b over 2. So this becomes b squared plus a, and this is squared. This is a plus b plus a over 3, and this becomes a squared plus 2ab plus b squared all over 4. And at this point, it's just some algebra, right? You have to put this together in the same denominator. Put this in the same denominator, you multiply by 4 on top, divided by 12, and then you multiply 3 on top here. This is 3a squared plus 2ab plus b squared all over 12. This would be 4b squared plus 4ab plus 4a squared minus 3a squared minus 6ab minus 3b squared all over 12. The 4a squared here, this becomes just a squared. This just becomes b squared. And this becomes minus 2ab all over 12. This is a perfect square trinomial. So this becomes a minus b parentheses squared over 12. So this is the variance for any continuous, uniformly distributed random variable on the interval from a to b. The variance is this constant, a minus b squared divided by 12. Okay, so today we discussed a new kind of random variable. They're continuous, and in particular, we spoke about the uniform random variable distributed, uniformly distributed on the interval a to b.